Here's the solution to one of the versions of quiz number 5 on series. The first question is about the geometric series, and we understand these exactly. There's a formula that tells us what they converge to, and they converge, and if the formula can't be applied, then that means we know that the series is divergent. The first part here is just to make sure you're reading the notation correctly, and there's still some of you who are having issues with this. I think maybe it's just the fact that the negative number is inside parentheses there, perhaps. But if we write out the first few terms of this, and remember the exponent in the denominator means repeated multiplication, so negative 3 squared means negative 3 times negative 3, which we know is positive 9. In the next term, that'll be negative 27, and in the next term, positive 81 in the denominator. So whatever that comes out to be. Just a point of notation, this is what we've been referring to as S4. The subscript here, the subscript here doesn't refer to the number of terms, rather it refers to the value of k for the largest term that we use. So if we, in our notation here, if we've used a value of k that's equal to 4 as our highest value, then that means that we're talking about S4. It doesn't matter much, but it does matter for the way we've stated the theorems on the remainder bounds. The exact formula for the geometric series, it has a formula that's the first term times 1 over 1 minus the ratio, as long as the ratio absolute value is less than 1. In this case, so the reason I wrote 2 ninths there was because that is the first term. We did figure that out already, so there's no reason to worry about that. To find the common ratio, we could take the ratio of 2 terms in a row. So I could take the second number I wrote up there divided by the first number, or I could take the third number divided by the second number, whichever way you want to do it. What happens in both cases is you get negative 1/3. So in our formula here, we have 2 ninths times 1 over 1 minus negative 1/3. So that's 4/3. So I have 2 ninths times 3/4, which is 1/6. In number 2, we're told to use the integral test. So the essence of the integral test is as goes the infinite integral, the improper integral, so goes the series. And I say it like that because they're not equal, but if one of them is convergent, then the other one has to be convergent. And if one's divergent, then the other one has to be divergent. So what it means is that as long as we can find the antiderivative for the integral, then we can see whether that's a finite number or not, and that'll tell us whether we should expect the summation, the series, to be a finite number or not. For this particular integral, we need to use a substitution. So u equals x squared plus 1, du will be 2x dx, and so 1/2 du equals x dx. So this will be all my substitution information over here. The integral then, if I change this over to be in terms of u, when x is 2, then u is 5. When the x is an n in the top bound, so here remember I'll use an n here. If x is n, then u is n squared plus 1. And the most important thing is I have 1 over u times x dx, and x dx is 1/2 du. So that 1/2 will factor out, antiderivative of 1 over u is log of u, and I'm evaluating that from 5 to n squared plus 1. And so I'll have 1/2 times the log of n squared plus 1 minus log of 5. The improper integral is value is going to be the limit of that as n goes to infinity. And of course, the only thing that's actually changing with respect to n here is this thing. So we can just sort of trace it through from inside out. If n goes to infinity, then n squared plus 1 is certainly going to infinity, and the log of inputs going to infinity will have outputs going to infinity. So this is infinity, so therefore the original series diverges. The relationship, the exact relationship between the series and the integral is actually illustrated in the in number 3. Realize that what we just showed was that this is equal to infinity. And so if this inequality is true, it says that the sum that I'm interested in is greater than something going to infinity. So that's why the integral test has us conclude that the series has to go to, that the series has to go to infinity, has to diverge. So the inequality you have in number 3 is exactly why finding the integral going to infinity is enough to know that the series diverges in number 2. The picture that we need to draw in number 3, we'd like to have the series be bigger than the integral. And so we know that we can represent the series using rectangles with base 1. And I'd like those rectangle areas to be bigger than the shaded area that I see, because the shaded area is this integral. So I need rectangles that are bigger than the shaded area. So that will be left rectangles. If you draw right rectangles, you'll see that they're not bigger. So you don't have to remember which one's which. Just think about which way do you want it to go. We would like the inequality to show that the rectangle area is bigger than the integral area, and so that's what will happen when we use rectangles like this. So this is the picture that that'll do it. So the area of this first rectangle is A2. Area of the second rectangle is A3, meaning those values when I plug into this formula. And so the sum of the rectangle areas is exactly the summation on the left. And we can see from the picture that the sum of the rectangles is bigger than the area under the curve.